Picture this. The year is 1928, and a quiet, kind of strange young man stands up and presents a new theory. And this theory, well, it was so deeply disturbing that it sent the world's most brilliant physicists into an absolute tailspin.
After hearing it, the legendary Werner Heisenberg called it the saddest chapter in modern physics. He almost walked away from the field entirely. Another giant of the era, Wolfgang Pauli, legend has it he actually did abandon physics, decided to go write a novel instead.
So what on earth could be hiding in a physics equation that was so terrifying? What kind of prediction could cause the smartest people on the planet to question the very fabric of the universe? Well, to really get why they were so scared, we've got to look at the problem he was trying to solve. Okay, so this young man was Paul Dirac, and he was trying to solve the biggest problem in physics, a problem we're honestly still wrestling with today: how to bring together two incredibly powerful but totally contradictory theories of reality.
See, on one side, you've got Einstein's relativity. That's the stuff that describes the universe of the really big and the really fast. And on the other side, you have quantum mechanics, the wonderfully weird probabilistic rules for the super, super small. The trouble was, they just didn't speak the same language. You try to describe something that's both tiny and moving incredibly fast, and both theories just completely fall apart. And look, this wasn't just some theoretical headache. The standard quantum equation at the time, Schrödinger's equation, it made predictions that were just flat out wrong. It said that gold should be a silvery gray color and that mercury ought to be a solid at room temperature. And why? Because in heavy atoms like those, the inner electrons are whipping around the nucleus at nearly the speed of light. Schrödinger's math just wasn't built for that kind of speed. It wasn't relativistic.
And this is where Paul Dirac comes back into the picture. Now, his colleagues called him the strangest man. They even had a joke that a Dirac was a unit of measurement for only saying one word per hour. But here's the thing about Dirac. He operated on this deep, fundamental belief that the laws of nature must be mathematically beautiful.
Now, other physicists had already tried to fix Schrödinger's equation. They'd cooked up this thing called the Klein-Gordon equation. But for Dirac, it was just ugly. It had these two massive flaws. First, it was clunky. You needed way too much info to get it started. But the real deal breaker, its math could lead to negative probabilities. I mean, think about that for a second. The chance of something happening being less than zero, Dirac had a very blunt assessment. It was physically nonsense.
So Dirac just started over from scratch with his search for beauty as his guide. He insisted that his new equation had to be simple, elegant, what physicists call first order. But when he tried to build it, he just hit a brick wall. None of the normal numbers he was using could make it work. And then he had this incredible stroke of genius. He remembered something his buddy Heisenberg had been playing with: matrices. These are basically grids of numbers where the order you multiply them in actually matters. And suddenly, he realized that if he used 4x4 matrices, all the puzzle pieces just clicked perfectly into place.
And what he created, oh, it was absolutely stunning. It wasn't just relativistic, it was beautifully symmetrical. For the very first time, an equation in quantum mechanics treated space and time as equals, exactly like they are in Einstein's universe.
And this equation was so powerful, it started making predictions all on its own. It turned out it needed a 4-part solution. Dirac looked at it and quickly saw that 2 of those parts perfectly described a weird quantum property called spin, this sort of built-in rotation that all electrons have. The crazy part? He wasn't even trying to explain spin. The equation just gave it to him for free. But that left a really haunting question. If 2 of the solutions describe the electron we all know and love, what in the world did the other 2 describe?
And this, right here, is where we get to the heart of it all. The real reason for all that despair. Because hidden deep inside Dirac's beautiful, elegant equation, there was a monster. You see, those other 2 solutions were for electrons with negative energy. Now, this wasn't just weird, it was downright terrifying. It meant that a normal electron could just keep falling into lower and lower and lower negative energy states, forever, spitting out infinite energy as it went. If that were true, every single atom in the universe should instantly collapse in a massive blaze of light. So let's be really clear about this. The most perfect, most beautiful equation that physics had ever produced was predicting a universe that was completely and fundamentally impossible. That was the ridiculous situation that drove Heisenberg crazy. It was a total masterpiece that described a reality that couldn't and shouldn't exist. For 3 long years, Dirac defended his equation. He was just so convinced that something so beautiful couldn't be wrong.
And then, in 1931, he came up with an explanation, and it was so radical, so bizarre, it sounded like it came straight out of science fiction. He suggested that maybe those negative energy solutions weren't a flaw at all. Maybe they were a prediction of a brand new type of matter, a particle he called the anti-electron. Dirac's big idea was that for every particle that we know of, there's a perfect mirror image twin, an antiparticle. It would have the exact same mass, but the exact opposite electrical charge. And if a particle ever ran into its antiparticle, poof, they would annihilate each other, vanishing in a flash of pure energy. Now, this sounds like pure fantasy, right? But then, just 1 year later, a physicist named Carl Anderson was looking at cosmic rays, and he accidentally snapped a photo of a particle track that was just unmistakable. It had the mass of an electron, but it curved the wrong way in his magnetic field. It had a positive charge. He had found it. He'd found Dirac's anti-electron, which he decided to call the positron. Think about that. From pure abstract math to a real physical discovery in just 12 months. Incredible. Okay, so Dirac's own explanation for why we don't see this stuff all the time was a little weird. It involved a whole sea of invisible negative energy particles. But a few years later, another genius physicist, Richard Feynman, came up with a much more elegant take. He showed that the math was telling us something even wilder. An antiparticle is just its normal matter twin traveling backward in time. I mean, let's not downplay this. Heisenberg himself called this the single biggest leap in all of 20th century physics. With just one equation, born from a search for mathematical beauty, Paul Dirac had revealed that our universe was twice as big as we ever imagined. For every single particle of matter, there was a hidden twin of antimatter, an entire anti-world, just hiding in the math. But you know how it goes in science. Solving one massive puzzle only revealed an even bigger one, a cosmic mystery that, to this day, physicists are still losing sleep over. So here's the final kicker. If you look at the Big Bang, it should have created matter and antimatter in perfectly equal amounts. And if that's what happened, they should have all found each other and canceled out completely, leaving behind a universe filled with, well, nothing but light. But that's not what happened, is it? For some reason we still don't understand, back in those first few moments, for every billion particle-antiparticle pairs that wiped each other out, just one lonely particle of matter was left over. Everything, and I mean everything, you see, the stars, the planets, you, we are all made of those cosmic leftovers. And that brings us to the final, profound question. In that very first battle between something and nothing, why was there an imbalance? Why did matter win? Why is there anything here at all, instead of just an empty void? And that, right now, is one of the greatest unsolved mysteries in all of science.